So chapter 13, the later chapters look at inductors in AC circuits. We've seen what happens with inductors when we put them in a DC circuit and how they behave. Now we need to see the behavior in an AC circuit because they behave quite a bit differently. We start looking at something called reactance instead of just the flow of energy through the devices. So our same types of key terms, but like I said, we're going to get to inductive reactance here. So in looking at it, we need to understand what goes on, what happens in an inductor when a sinusoidal voltage and current are presented. An inductor passes AC with an amount of opposition called inductive reactance. Okay, we saw this in capacitors where we saw the capacitive reactance. Now we need to look at the inductive reactance, and we're going to see as we move forward with inductors and capacitors in circuits, RLC circuits, we're going to find out that circuits become what are called tuned circuits, and they will then start exhibiting properties where we can filter specific signals at specific frequencies by having inductors and capacitors of the right value and applying the correct source voltage and current. So the inductive reactance depends on the frequency of the alternating current. The concept of the derivative then was introduced in chapter 12, and we saw that di by dt and dv by dt, and we'll see those play out. The expression for induced voltage in an inductor also was stated earlier. So we need to look at now what happens with the phase relationship with current and voltage in an inductor. So get used to looking at these waveforms and what's going on here. You can see just from a quick inspection the difference between the current waveform and the voltage waveform. We can already see that we have a phase difference between the two. So the formula that we previously introduced for induced voltage, we can see that the faster the current through an inductor changes, the greater the induced voltage will be. Okay, so there we go. We can also see over here we've got a phasor representation that we need to become familiar with, and there's our formula V sub L, the inductor voltage, induced voltage, L di by dt. For example, if the rate of change of current is 0, the voltage is 0. Again, just applying it mathematically to that relationship. When di by dt is a positive going maximum, the voltage induced is a positive maximum. When di by dt is a negative going maximum, the induced voltage is a negative maximum. So we can see that over here in our waveforms. A sinusoidal current always induces a sinusoidal voltage in inductive circuits. Therefore, you can plot the voltage with respect to the current if you know the points on the current curve at which the voltage is 0 and at which point it is a maximum. The phase relationship then shown in the diagram, notice that the voltage leads the current by 90 degrees, and we can see that here in the phasor diagram. Voltage on the horizontal axis, current on the vertical axis. We notice that there is a 90-degree phase difference between them. Okay, and this, you notice the red line matches the current sinusoidal waveform. Blue line matches the blue voltage sinusoidal waveform. So the current and voltage of this relationship then can be shown in a phasor representation. So just like capacitive inductance, we need to understand capacitive reactance, we need to understand inductive reactance. In this case, X sub L. You'll recall we used X sub C in the previous chapter. Inductive reactance is the opposition to sinusoidal current. And we use, again, the value of ohms. And this is what we need when we develop our relationships and our mathematical analyses. Everything has to be in the same unit, so it is transformed through inductive reactance to ohms. The symbol for inductive reactance then being X sub L. To develop a formula for X sub L, we use the relationship the induced voltage is equal to L di by dt. And the curves in the figure 1331, the rate of change of current is directly related to the frequency. And we can see that as we develop, just like we did for the RC. You'll notice the difference between waveform A, waveform B, the slope here being depicted in the sinusoidal waveform. The slope of a sine wave A at the zero crossing is steeper than that of the sine wave B. Recall that the slope of a curve at a point indicates the rate of change of that point. Okay, so just like in our fundamental understanding of the slope in math, now we apply it in electronics to a inductive circuit. Recall that the slope of a curve at a point then indicates that rate of change. Sine wave A has a higher frequency than sine wave B. And again, we can see that by inspection. Okay, we've got two iterations, two complete cycles to one complete cycle of B. When frequency increases, di by dt increases. And thus the induced voltage increases. When frequency decreases, di by dt decreases, and thus the voltage induced decreases. Okay, so again, you can think about that slope just like the rise over the run in your math class. We've got the change in current with respect to time. The induced voltage then is directly dependent on frequency. The induced voltage increases as di by dt, the slope increases. The voltage induced decreases as the slope di by dt decreases. An increase in induced voltage means more opposition, so X sub L becomes greater. Therefore, X sub L, the inductive reactance, is directly proportional to induced voltage and thus directly proportional to frequency. When one goes up, the other one goes up. Okay, it's not like an inverse proportion where one goes up, the other goes down. X sub L then is proportional to frequency. Now, if di by dt, the slope is constant and the inductance is varied, an increase in inductance produces an increase in the induced voltage, and a decrease in inductance produces a decrease. Okay, and just think of it as, as a multiplier. Okay, so when we have our multiplier by the slope, it's going to act in unison correspondingly. Again, an increase in induced voltage means more opposition, greater resistance, greater X sub L. It's just resistance, it's in ohms. Therefore, X sub L is directly proportional to induced voltage and thus directly proportional to inductance. So one goes up, the other side goes up. The inductive reactance then is directly proportional to both the frequency and the inductance, so it's proportional. The formula derived in Appendix B for inductive reactance is, and now here's our formula, our handy dandy formula. Remember, we had the one for X sub C, 1 over 2 pi F L FC for capacitance, now for inductance. We have no inverse proportionality. Inductive reactance, X sub L in ohms, when the frequency is in hertz and the inductance is in henries. As with capacitive reactance, the 2 pi term is a constant factor. Okay, it's just tying in the periodicity of the sine wave going from 0 to 360 or 0 to 2 pi, which comes from the relationship of a sine wave to rotational motion. So Let's take a look at a quick example here. A sinusoidal voltage is applied to a circuit. The frequency is 10 kHz. Determine the inductive reactance. So we can see here it's very simple. No resistor in this circuit, just an inductor and an AC source. We're going to convert 10 kilohertz to its exponential. So it's 10 times 10 to the third hertz, and 5 millihenries converted becomes 5 times 10 to the minus 3. Okay, here again, mathematically, they made it simple. 10 to the minus 3, 10 to the third, they cancel out. One subtracts from the other because we know we add the exponents. Therefore, the inductive reactance, when we put them together, becomes simply 2 pi times the frequency times the inductance. The tens to the thirds and minus thirds disappear. We end up with 314 ohms. Okay, so simple example, but it drives the point home. When we come back, we'll take a look at the reactance in series and parallel inductors.